Consider a collision between a moving 7-ball and an 8-ball that is at rest in the sport of table pool. When the 7-ball collides with the 8-ball, each ball experiences an equal force directed in opposite directions. The rightward moving 7-ball, the rightward moving 7-ball experiences a leftward force that causes it to slow down. The 8-ball experiences a rightward force that causes it to speed up. Since the two balls have equal masses, they will also experience equal accelerations. In a collision, there is a force on both objects that causes a collision. It causes an acceleration of both objects. The forces are equal in magnitude and opposite in direction. For forces between equal mass objects, each object experiences the same acceleration. You know what it's saying, guys? Have you guys ever played pool? You guys probably have played pool. You know when you strike a ball really nicely, and it's obviously the 7-ball doesn't hit the 8-ball very often, especially by design. But when you take your cue ball and you strike a ball really nicely, what does the cue ball do afterwards? If you strike it really in the center of it, the cue ball is going to want to stop right where you hit that last ball. What happens, guys, collisions, objects of equal masses that collide trade velocities. That's what happens. The one ball goes from moving to rest. The ball at rest goes from at rest to moving with the same velocity as the ball that you hit. They trade velocities. In pool, anything else that the cue ball does after it hits is due to the angular momentum, is due to it being hit at a different angle with spin on it, anything like that, or not striking the ball directly. Like if it strikes the side of that 8-ball, like what Gio and Dennis said, it's going to bounce off to the side or something like that. Also, depending on what kind of spin you put on your ball, that will determine what happens to the ball afterwards. More experienced pool players will hit the top or bottom of the cue ball to create top spin or backspin after they hit it in order to collide with other balls. But a true and honest hit results in the trading of velocities. You hit the bottom of the ball with enough force, it'll create backspin, and your cue ball will roll back towards you. You hit the top of the ball, it'll follow on through and hit balls further down the table. But for collisions between equal mass objects, each object experiences the same acceleration. That's another way for saying they trade velocities. One of the most powerful laws in physics is the law of conservation of momentum. The law of conservation of momentum can be stated as follows. For a collision occurring between object 1 and object 2 in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. That is, the momentum lost by object 1 is equal to the momentum gained by object 2. The above statement tells us that the total momentum of a collision of objects, a system, is conserved. That is, the total amount of momentum is a constant or unchanging value. This law of conservation of momentum will be the focus of the remainder of the lesson. Consider a collision between two objects, objects 1 and 2. For such a collision, the forces acting between the two objects are equal in magnitude and opposite in direction. This statement can be expressed as follows. F1 equals negative F2. And you can really say that F1 equals F2. The negative is there to show that F2 is happening always in the opposite direction. The forces act between the two objects for a given amount of time. The time that the forces act on each object is always going to be equal. You're never going to be able to have object 1 acting on object 2 for a longer time than object 2 acts on object 1. So T1 equals T2. Since the forces between the two objects are equal in magnitude and opposite in direction, and since times for which these forces act are equal, it follows that the impulses experienced by the two objects are also equal and opposite. As an equation, this can be stated, force times time 1 equals negative force 2 times time 2. You guys know that force times time is the impulse, so saying that the forces are equal and saying that the times are equal must mean that the impulses are equal as well. But the impulse experienced by an object is equal to the change in momentum of that object, due to the impulse momentum change theorem we just learned about. Thus, since each object experiences equal and opposite impulses, it follows logically they must also experience equal and opposite momentum changes. As an equation, this can be stated m1 times delta v1 equals negative m2 times delta v2. The above equation is one statement of the law of conservation of momentum. In a collision, the momentum change of object 1 is equal to and opposite the momentum change of object 2. That is, the total momentum lost by object 1 is equal to the total momentum gained by object 2. In most collisions between two objects, one object slows down and loses momentum while the other speeds up and gains it. If object 1 loses 75 kilogram meters per second of momentum, then object 2 gains 75 kilogram meters per second of momentum. Yet the total momentum of the two objects is the same before and after the collision. The total momentum of the system is conserved. A useful analogy for understanding momentum conservation involves a money transaction between two people. Let's refer to the two people as Jack and Jill. We checked the pockets of Jack and Jill before the transaction, and they both possessed $100. That means the total amount of money of the two people before the transaction is $200. During the transaction, Jack pays Jill $50 for the given item being bought. There is a transfer of $50 from Jack's pocket to Jill's pocket. Jack has lost $50 and Jill has gained it. The money lost by Jack is equal to the money gained by Jill. After the transaction, Jack now has $50 in his pocket and Jill has $150. Yet, the total amount of money of the two people after the transaction is $200. The total amount of money before the transaction is equal to the total amount of money after the transaction. It could be said that the total amount of money of the system is conserved. It is the same before and after the transaction. So let's use us as an example, right? We all have $5 in our pocket. And Del Val lunch ladies have $0 because we haven't all bought lunch yet. And then how many of us in the classroom are there? 6 total? So then the 6 of us go spend our $30 on lunch and we don't have any money in our pockets anymore. We all went from $5 to $0. The lunch ladies, however, went from $0 to $30. And if you look at the community as a whole, this classroom and the Del Val lunch people, we had $30 before and $30 after. The total amount of money in the community never changed. Same thing like when you go buy something at a store. It gets out of your pocket and goes into Mr. Walmart's pocket. The total amount of money doesn't change. There's always been $200 or obviously way more than that. But you spent $200, you have $200 less, and you spent it on Mr. Walmart's stuff. He has $200 more. Is the founder of Walmart, is his name Sam? Why do I think that's right? I was just in my head, that was correct. So look at this little chart here, this table. Jack before had 100, Jill before had $100, total $200. After, Jack has 50, Jill has 150, total is still 200. The change is going to always equal 0 out down here. It is, right? What's his last name? Sam Walden? Yep. I thought I knew that. You tell me something once and I usually remember it for a very long time. The table shows the amount of money possessed by the two individuals before and after the interaction. It also shows the total amount of money before and after the interaction. Note that the total amount of money is the same before and after. It is conserved. Finally, the table shows the amount of change in the amount of money possessed by the two individuals. The change is equal to and opposite of the change in Jill's account. For any collision occurring in an isolated system, momentum is conserved. The total amount of momentum of the collection of objects in the system is the same before the collision as after the collision. A very common physics lab involves the dropping of a brick upon a cart in motion. The dropped brick is at rest and begins with 0 momentum. The loaded cart is in motion with considerable momentum. The actual momentum of the loaded cart can be determined using the velocity and the mass and multiplying them together. The total amount of momentum is the sum of the drop brick's momentum and the loaded cart's momentum. dropped brick not having been dropped yet at rest, its momentum is 0. The loaded cart is moving with a certain momentum. After the collision, the momenta of the two separate objects, the dropped brick and the loaded cart, can be determined from their measured mass and velocity. If the momentum is conserved during the collision, then the sum of the dropped bricks and the loaded cart's momentum after the collision should be the same before. The momentum lost by the loaded cart should equal or approximately equal the momentum gained by the dropped brick. Momentum data for the interaction between the dropped brick and the loaded cart could be depicted in the table similar to the money table above. So before the collision, the dropped brick was at rest and had 0 units of momentum. The loaded cart was moving with a mass, so it had 45 units of momentum, whatever velocity and mass it was going at. Then after you drop the brick on the cart, the whole thing is moving slower. That cart slows down. It loses momentum. See how it went from 45 to 31? Because that cart slowed itself on down. The dropped brick, however, sped up. It was not moving, and you dropped it on the cart, and now it's moving. So the lost momentum by the cart, 45 to 31, equals the gained momentum from the brick, 0 to 14. 14 units of momentum gained, 14 lost. Total momentum, always 45 units. Even though the object slowed down, momentum is directly proportional to both mass and velocity. Even though the object visibly slowed down, it weighed more, so it didn't have to go as fast to get the same momentum. Collisions commonly occur in contact sports such as football and racket and bat sports such as baseball, golf, or tennis. Consider a collision in football between a fullback and a linebacker during a goal line stand. The fullback plunges across the goal line and collides in midair with the linebacker. The linebacker and fullback hold each other and travel together after the collision. The fullback possesses a momentum of 100 kilogram times meters per second east before the collision. The linebacker possesses a momentum of 120 kilograms times meters per second west before the collision. The total momentum of the system before the collision is 20 kilograms times meters per second west. Therefore, the total momentum of the system after must be 20 kilograms times meters per second west. The momentum must be conserved. The fullback and the linebacker move together as a single unit after the collision with the combined momentum of 20 kilograms times meters per second. Momentum is conserved in the collision. If you use some sort of vector diagram and draw an arrow with the length of the amount of momentum that object has, if you see the linebacker's arrow is slightly larger. This reminds me of balancing force diagrams in our last unit, right? Like you looked for the arrow that was slightly longer, and that's the way it was unbalanced in. Same thing here. Momentum, linebacker has slightly more momentum. He is slightly moving with more momentum. Either he weighs more or is moving faster, some combination of the two. And afterwards, they have a slight momentum the other way. Now suppose that a medicine ball is thrown to a clown who is at rest upon the ice. The clown catches the medicine ball and glides together across the ice. The momentum of the medicine ball is 80 kilogram meters per second before the collision, and the momentum of the clown is 0 meters per second before the collision. The total momentum of the system before the collision is 80 kilogram meters per second. Therefore, the total momentum of the system after the collision must also be 80 kilogram meters per second. The clown and medicine ball move together as a single unit after the collision with combined momentum of 80 kilogram meters per second, and momentum is conserved. I want to go back up to this one with the football players. That fullback must be moving at a decent speed to get 100 kilogram meters per second of momentum, and same thing with that linebacker. He must be moving at a decent speed too. The amount that they are moving after, though, is very slow in the backwards direction compared to each direction they were moving before. That is because their masses as a combined unit are more than they were individually before. So you had 100 kilogram meters per second for the fullback, 120 for the linebacker before at their respective masses, and then combined You combine their masses, well, to get 20 units of momentum with two people, you're not going to be needing to move nearly as fast as you would for 20 units of momentum with one person. I want you guys to watch this. Watch what happens to the velocity of the cart after it collides with the red cart.
We will observe an inelastic collision between two carts of an equal mass. One of the carts, the red cart that you see in the center of the video, has a mass of 750 grams or 0.750 kilograms. The blue cart, which will be moving into the scene, has a mass of 0.250 kilograms or 250 grams. The collision will be an inelastic collision in which these two carts stick together and move as though they were a single object after the collision. So before the collision, all of the momentum will be concentrated in the blue cart, which has a mass of m, and afterwards, together, the two carts have a mass of 4 times the original mass. The 3m for the red cart and the m for the blue cart add up to a total m of 4m. So the collision looks something like this. In the background of this video, you'll notice that we have a position time graph. And the position time graph was obtained by setting a motion detector to detect the motion of the blue cart. And somewhere around this point on the graph, we observe that the collision takes place. The velocity of the blue cart, as represented by the slope of the line, changes dramatically at that point. We can use the tools of this program in order to determine the pre-collision and the post-collision velocity of the blue cart. Right here is the moment just before the collision. And if I use the tool that calculates the slope of that line, I will find that the blue cart was moving before the collision with a speed of approximately 0.5022 meters per second. After the collision, right around here, the speed of the blue cart and red cart was the same, and we can determine its speed by using the tools of this program. And what we find is that after the collision, the speed is then 0.1295 meters per second. This is roughly 1/4 of the original speed. This proves to me that momentum is being conserved, that before the collision, the blue cart with a mass of m had a velocity of v, which was about 0.5022, and after collision, the total momentum was concentrated in both carts, which had a mass of 4m and was moving with a velocity of roughly 1/4 v. The 0.1295 is roughly 1/4 the 0.5022 meters per second.
Okay, so what we saw, guys, was that blue cart was moving with a pretty good speed, and then it hit the red cart, and together they moved pretty slow. The red cart was at rest. It had no momentum. The blue cart was moving pretty quick. It had all the momentum. Total momentum of the system before and after the collision needs to be the same. So now that both carts are moving, they don't need to hit as high of a velocity in order to carry that much momentum. The mass increases, the velocity doesn't need to increase by as much in order to hit the same amount of momentum. P equals mv. There's some understanding questions here I want you guys to try and answer. Maybe just throw them around the room and see what you guys think. When fighting fires, a firefighter must use great caution to hold a hose that emits large amounts of water at high speeds. Why would such a task be difficult? Any ideas? Go ahead, Gio.
Looks like if the water's shooting out of the hose so fast and like give you like a pullback or something.
Exactly. Gio said the water is shooting out of the hose so fast, there's going to be some backwards force, some reactionary backwards force. That's exactly right. The hose is pushing lots of water, which has a large mass, forward at a high speed. This means the water has a large forward momentum. In turn, the hose must have an equally large backwards momentum, making it difficult for the firefighters to manage. You ever see like I don't know, it's more like a cartoon or something when like the firefighter loses control of the hose and it flies backwards and starts spraying everywhere. That's what's going on there. There's forward momentum, and a big strong firefighter, has to stay and counteract, provide the backward momentum for the hose. A large truck and a Volkswagen have a head-on collision. Which vehicle experiences the greatest force of impact? Gio says the Volkswagen. I think they're equal. Forces are going to be equal and opposite. Which vehicle experiences the greatest impulse? Well, if impulse is force times time, and the forces are equal and the times are equal, then the impulses are going to have to be equal. Which vehicle experiences the greatest momentum change? Well, impulse equals a change in momentum. So if I just told you that because the forces and the times are equal, that the impulse was equal, then the momentum change must be equal too. What about the resulting acceleration? Which vehicle experiences the greatest resulting acceleration? Think about what they say here about acceleration. A, if F equals ma, Newton's second law, A equals F over m. So directly proportional with force, acceleration, inversely proportional with mass. Summer, you want to give a guess here for which vehicle experiences the greatest acceleration? You just unmute your mic. The truck or the Volkswagen?
Maybe a Volkswagen.
That is exactly what I wanted you to say. That's exactly correct. Really good job. Summer knew that even though the forces were equal, the impulses were equal, and the momentum was equal, that the Volkswagen is going to experience the greatest acceleration just because it has a smaller mass. So A, B, and C, both the Volkswagen and the large truck encounter the same force, the same impulse, and the same momentum change. But the acceleration is greatest for the Volkswagen, because even though everything prior discussed was the same, the acceleration for the Volkswagen is greatest due to its smaller mass. These puns kill me. I do, and not in a good way. I do have to say they're not good. Miles to go and Ben traveling are riding in a bus at highway speed on a nice summer day when an unlucky bug splatters onto the windshield. Miles and Ben begin discussing the physics of the situation, and Miles suggests that the momentum change of the bug is much greater than that of the bus. After all, argues Miles, there was no noticeable change in the speed of the bus compared to the obvious change in the speed of the bug. But Ben disagrees entirely, arguing that both the bug and the bus encounter the same force, momentum change, and impulse. Who do you agree with? Guys online, I want you guys to send me a message saying who you agree with here. You can reread it if you need to, Miles or Ben. And then you guys just decide yourselves. I'll ask you guys in a second. All right, I have a pretty big split from my online students. Clara, who do you agree with, Miles or Ben? John? Michael? Okay, that's okay too. Dennis? You don't know? Gio?
Yeah.
Ben? Ben is correct. The bug and the bus experience the same force, the same impulse, and the same momentum change. This is contrary to the popular, though false, belief which resembles Miles' statement. The bug has less mass and therefore more acceleration. Occupants of the very massive bus do not feel the extremely small acceleration. Furthermore, the bug is composed of a less hardy material and thus splatters all over the windshield. The greater splatterability of the bug and the greater acceleration do not mean the bug has a greater force, impulse, or momentum change. So the mass of the bus being thousands of times larger than the mass of the bug means that the acceleration change that the bug endures will be thousands of times more than the bus. The bus actually does slow down when a bug hits. It is just so infinitesimally small because of the larger mass, we don't notice, see it, anything like that. I think although be it like a sci-fi example, if you had like a bug, a regular sized bug hit the bug gets smushed and it changes its velocity, it has acceleration, but it's so tiny. And then if you thought about a giant bug, the biggest, like a Godzilla sized bug, and the bus hits that, then it's reversed. The bug's velocity doesn't change because he's so gigantic and enormous, and the bus gets crushed and smushed. It's whoever's bigger does not experience the acceleration, does not feel the acceleration like the smaller, less massive object.
Would it be the same thing if like someone was running and they got a bug in their eye or something like that? Like
Yes, if someone's running and they get a bug in their eye, it doesn't hurt because of physics. It hurts because having bugs in your eyes hurt.
yeah, but like I'm talking about
Yes, that person slows down. They actually do slow down an infinitesimally small amount. If Bug and Geo are running at opposite directions and the bug flies into Geo's eye with all of its force, the bug slows down a lot and splatters or whatever it does, and Geo does slow down the tiniest bit. It's infinitesimally small, it's almost non-calculable, but it does happen according to Newton's second law, third law as well. A little combination of both of those. Let's try this one. If a ball is projected upward from the ground with 10 units of momentum, what is the momentum recoil of the Earth? Remember the law of conservation of momentum. If the law of conservation of momentum holds true, and the ball and the ground and the Earth are all part of the same system, then the ball goes from rest and gains 10 units of momentum, so the Earth must lose 10 units of momentum downward, recoil. The Earth recoils with 10 units of momentum. This is not felt by Earth's occupants since the mass of the Earth is extremely large. The recoil velocity of the Earth is extremely small and therefore not felt. When you throw a ball upwards, the Earth recoils backwards with the same momentum. We just don't feel it because of how massive the Earth is. Let's look at this one. They throw math in there for us. If a 5-kilogram bowling ball is projected upwards with a velocity of 2 meters per second, then what is the recoil velocity of the Earth? Well, the 5-kilogram bowling ball going upwards at 2 meters per second, P equals mv, means that the momentum must be 10 kilogram meters per second. But then the recoil velocity of the Earth is not the same as the recoil momentum of the Earth. Watch. Since the ball has an upward momentum of 10 kilogram meters per second, the Earth must have a downward momentum of 10 kilogram meters per second. To find the velocity of the Earth, use the momentum equation P equals mv. This equation rearranges to V equals P over m. By substituting into this equation our 10 kilogram meters per second and our mass of the Earth, 6 trillion billion kilograms, it looks like, 6 times 10 to the 24th, we get a velocity of 1.67 times negative 10 to the 24th downward. Another way to write the velocity of the Earth is to write it as about 21 zeros and then 167 meters per second. So the Earth does recoil when we throw things up from it. The Earth does have a recoil momentum and a recoil velocity. But the mass of the Earth is so large that we do not feel it.